Guys, this video is going to help you answer questions 1 through 5. This is your week 7 lesson. Okay, so before we get started, we're going to review what we learned last week, the difference between mechanical and electromagnetic waves. So there's two major categories of waves, mechanical and electromagnetic. Mechanical waves always need matter or particles of a medium through which to travel. Sound waves are just one type of mechanical wave. If sound energy doesn't have a medium through which to travel via a wave, then it can't move from its source to another location. And that's what we watched in the video about the two cell phones in the bell jar. So phone B lit up inside the jar, but you couldn't hear the sound once all the air had been removed. Since there was no matter or medium inside that bell jar, even though the phone was ringing, there was no way for the sound energy to be transported to our ears, so we couldn't hear anything. But light waves are different. There is only one type of they are electromagnetic waves. Although they can travel through air or other matter, they don't need a medium in order to travel. Think of space. Light from the sun is able to move through empty space to reach Earth. This is one way that scientists know that light doesn't need a medium. And the same thing was true for phone B inside that bell jar with no air. Even though we couldn't hear phone B ringing, we could still see it light up. And that light from the phone B didn't need a medium to be transported. So mechanical waves, like sound waves, must have a medium in order to travel. And electromagnetic waves, like light waves, can travel whether they have a medium or not. All right, we're going to review sound waves really quickly.
Whoa, Sam! That sculpture's amazing! How do you balance all those things?
Just gotta be very careful. Oh, no!
That jackhammer's making the whole table shake!
I know! It's so loud I can feel it!
Phew, it stopped. But not before ruining your sculpture. Sorry, Sam. Just goes to show, sound is more than just what you hear. It's a whole world of vibrations.
How can sound be vibrations? It's noise.
Check it out. When you clap your hands together, or when that jackhammer hits the ground, it makes air move. In waves. Sound waves, to be exact.
Like ocean waves?
Well, kind of. Sound waves travel through the air, but they carry energy like ocean waves do. That energy is what makes an echo.
Really?
Definitely. When moving sound waves hit a surface, like a mountain or even a wall, the energy bounces off and comes back at us. That's the echo.
Cool.
But there's much more to sound waves than just energy. They have different pitches, frequencies, and volumes.
Huh? You're losing me.
Okay, think about the gazillion sounds around us.
Yeah, like birds sound totally different from gorillas, and tea kettles sound different from tubas.
Right. Their sounds have different pitches, high and low.
So what makes them that way?
High-pitched sounds have a high frequency. That means their sound waves vibrate quickly, and there are lots of waves per second, so we hear a higher pitch.
And low-pitched sounds have a low frequency?
Right. Fewer waves per second.
Well, that jackhammer was definitely low, but it was also loud. Wouldn't that make it a high frequency?
Not quite. Volume's a totally different thing. It's the loudness or softness of a sound. The louder the volume, the higher the wave. That's called amplitude.
Like altitude, only for sound. So, how loud is that jackhammer? I mean, compared to other things.
I'd say it's about 105 decibels.
Decimals?
No, decibels. Volume's measured in decibels. The louder the sound, the more decibels. An airplane taking off is 140 decibels, and a crying baby is 110.
Whoa, no wonder my little cousin gives me a headache. I gotta teach him how to whisper.
Yeah, a regular conversation's about 65 decibels, but whispering's only 0 to 5.
Hey, are there any sounds that are lower than 0 decibels?
Yep, humans can't hear them, but we think animals can. They're caused by giant explosions or waves in the ocean. In fact, scientists are studying them,
For what?
To help us predict when a volcano might erupt or if a tsunami's coming.
I can't believe how much goes on behind the scenes when it comes to sound. Who knew that sounds are vibrations that travel in waves, and that frequency tells us the number of waves in a second? It makes sense that frequency goes with pitch, or the highness or lowness of sounds. The volume of a sound is how loud or soft it is, and is measured in decibels. High sounds, low sounds, birds, and bass guitars.
Speaking of noise, it sounds like that jackhammer's done for the day. How about I help you put your sculpture back together?
Wow, thanks. That'd be great. I'll just put on some music.
Sam, remember what happens with loud sounds?
All right. How about we try some classical music?
Okay, so in summary, sound is caused by vibrations. Sound travels in waves. Frequency is the number of times the sound wave repeats in a second. Pitch is the highness or lowness of sounds, and volume is the loudness or softness of a sound and is measured in decibels. So our focus question for questions 1 through 5 is, how do sound waves behave when they interact with matter? So when they interact with a solid, a liquid, or a gas. So sound waves can be reflected, they can be absorbed, and they can be transmitted. If you look in the picture to the right, this arrow is representing sound being transmitted through the air. This blue arrow is representing sound being reflected off of the ceiling, and this blue arrow in the ceiling itself is representing the absorption of sound. When a wave passes through a medium, that's called transmission. If you click on this link, and I'll share the PowerPoint with you, you can actually try this out. I have a lab that you can do at home with just simple materials that you can find in your house. Sometimes a wave bounces off something, which is called reflection. I also have a lab that you can do at home to try this out. And sometimes a wave doesn't pass through something, but instead it's absorbed. And again, I have a mini lab that you can do to try this out. And this happens when the particles of matter take in some of the wave's energy instead of passing it on. So I don't want to get into too much of it because I'd like you to try out the lab, but it has to do with opening and shutting a door. So like if you were to talk through something, say the water, or like in a pool or a door, some of the sound will get absorbed instead of being passed through, which makes the sound seem higher or lower in volume depending on how you're speaking through the door, and how it just sounds overall. So sound waves can also be transmitted through solids, liquids, and gases. Passing from one medium to another causes a change in the sound wave. So if you go from the air to a liquid, it actually changes how the sound sounds, and it changes its speed. If you go from a liquid to a solid, or a solid to a liquid, or a gas to a solid, so just changing from one medium to another, it doesn't matter what the medium is, the sound will change in overall quality and speed. So often the waves change direction when they pass from one medium to another, and we call that refraction. We'll go over more about what refraction is when we talk about light waves. Usually when a wave interacts with matter, there is some combination of all of these processes happening. One thing just doesn't happen. So I'm talking right now, and the sound from my voice is being absorbed by the materials around me. It's being reflected off of the walls in my house. And it's probably being transmitted. It is being transmitted. It's being transmitted through the air, but it can also be transmitted through the walls. There's a wall right behind my couch, and if somebody was in that next room, they probably could hear a little muffle of my voice. Here is the try it out, the two experiments that I wanted you to do for the try it out. So for reflection, what you could do is you could get 2 paper towel tubes and get a board and line the paper towel tubes up like you see in the picture, and put like a watch or something that moves like on a battery, and then put your ear on the other end, and you will hear the watch through the tube bouncing off the board. So you can try it out and see if you can hear sound reflecting. And then to try out transmission and absorption, Try talking to a family member between a door. So open the door and then try talking again. And you should notice a difference in the sounds that you hear. There is another lab that you can do where you can experience all three at the same time, transmission, reflection, and absorption. So if you have a wire hanger at home and two pieces of string, it can be a tennis shoe string, it can be yarn, it can be kite string, it can be any kind of string you have. And you can tie the two strings to the ends of the hanger upside down. And if you wind the string around your fingers and stick them to your earlobes and then bang. I know this sounds weird, but hit that wire hanger against an object and experience the sound you hear. It is so much different than hearing the sound of the wire hanger without the string. So those are just a couple things for you to try out to experience what happens when sound does interact with matter. Okay. So let's look at architectural acoustics.
When sound impinges on a surface, like that found on a building's interior, some of the energy passes through. Some of the sound energy is absorbed and reassigned as heat within the material. Ah! You can't make the wall hot by yelling at it. It's not that much heat. There are molecules inside the building material, and when they are impinged upon by the sound energy, they move, and as they rub together, they lose some of the energy through friction. Finally, some of the energy is reflected. All three are happening simultaneously: transmission, absorption, and reflection. We can also model it like this.
All materials transmit, orbit, and reflect sound.
Not in this universe. It's transmit, absorb, and reflect sound.
Yeah, that's what I meant.
Of course you did. This is a function of the material mass, surface smoothness, fiber orientation, porosity, airtightness, and stiffness. Let's look at a material with little mass and a surface with negligible pores. Say glass. We'll put glass on top. Watch as sound impinges on the glass. Lots of energy transmitted, not much mass to the glass, not much absorbed in the surface of the glass, few pores and therefore few corresponding air pockets. Simultaneously, we'll look at concrete. Smooth concrete. Much more mass, and provided the concrete barrier is airtight, absent penetrations, very little will transmit through the barrier.
Notice the difference in the two mediums. So more sound was actually able to go through the glass than the concrete wall. So the material, it changes the speed, but it also changes the direction too. And so we build structures because they provide functions. And we'll talk more about that in a minute.
Because the concrete surface is smooth, there is little absorption and high levels of sound reflection. Finally, we'll add a third barrier. We'll start with the concrete wall and add a layer of fabric-wrapped glass fiber to it. The mass of the concrete restricts the sound energy transmitting through, but the pores in the glass fiber absorb a good deal of the sound, so that relatively little is transmitted and relatively little is reflected.
Which one is best?
Well, it depends. Generally, we have little use for barriers that allow sound to travel into a building or through buildings, so usually less sound transmission is a worthwhile goal. But the proportion of sound that is reflected relative to the proportion that is absorbed, that decision is the subject of the next series of animations.
So the video shows several examples of everyday objects that were designed with a specific goal related to sound. Actually, I don't think that video did, but we can talk about some examples that have a specific goal. So a stethoscope is what doctors wear to listen to your heart beat in your lungs, and that's designed with a specific function in mind. And the material that's used to make the stethoscope, we have to take that in consideration. Concert halls. So what we build concert halls with, we have to be very careful and take into consideration the materials, because we want that sound to stay in the concert hall. We don't want it to be transmitted through the walls. And so the material that we use to build concert halls and cafeterias and houses, architects have to take that into consideration. Engineers have to take that into consideration when they're building things, dependent upon what the goal of the device is. So understanding the way that sound waves interact with different types of matter allows us to design things like buildings and rooms and instruments and speakers so they function in a specific way. This is just an example of how structure and function are related. Structures can be designed or changed so that their function meets a goal. If the goal is to make a classroom in a school more soundproof so the students can concentrate better, then the walls, the structure, need to be built in a way that make that function possible. So, can you think of structures and function examples and describe the sound wave and matter interactions that allow the structure to match the function? I've come up with some examples to talk you through. So, maybe if you're struggling, this might be helpful. Or maybe this is what you thought of. So, what is happening? Oh. Okay, so over here, we have a thick concrete wall in the classroom. Its function is to minimize the amount of sound that enters and leaves the room. And the sound wave matter interaction, the thick concrete walls would absorb and reflect sounds, but not transmit them. Foam earplugs that fit in your ears. These protect your ears from loud sounds. The earplugs would transmit some sound waves so that you can hear some sounds, but they're going to absorb most of them and reflect most of them, so they protect your eardrum from too much vibrational energy. If you've ever noticed in the cafeteria at school, if you look up, there's all those college banners hanging in the cafeteria. That thick fabric in the banners help control the volume level when the cafeteria is crowded. So they're not just there for decoration. Those fabric banners will absorb some of the sound waves in order to reduce the volume and reduce the amount of sound waves that are reflected and transmitted. This is another reason why classrooms are decorated so much. We've got fabric curtains hung up and posters and plants and just furniture. And all of those things are helping to absorb the sound so that it doesn't get so loud in that classroom. Another example of structure and function would be a movie theater. So in a movie theater, those walls are specifically designed so that you don't hear sound in the next theater. Now, I don't know about you, but I think that they could use some work, because when I go to the theater, I still can hear some sound from the next room. So I think our engineers need to get to work on that and see about improving and making that structure better for its function. Okay, I must have really messed this up. Okay, so ending talking about sound waves and how they interact with matter. So how do sound waves behave when they interact with matter? Well, sound waves can be reflected, they can be transmitted, and they can be absorbed. Depending upon the material, the speed will change, and so will the direction. And I'm going to stop there so that you can answer questions 1 through 5.